Good morning, everyone. I am Jonbert, Jude, Esoto, and I am be reporting here about Ohm's law, most especially of the three following circuits, which are the purely resistive circuits, the purely inductive circuits, and the purely capacitive circuits. So, our main objectives for these three topics are to describe with diagrams and equations the phase relationships for circuits containing pure resistance, pure inductance, and pure capacitance. And also, we will try to apply Ohm's law in the purely resistive AC circuits, the purely inductive AC circuits, and the purely capacitive AC circuit. So, let's start our discussion with the purely resistive circuits. So, as you can see in the diagram, we have an AC source and a resistor. In here, I will only discuss what is the property of the resistor when it is applied in an AC source. And also, so let's try to look at the diagram. As you can see, the voltage is in phase with the current. We will be also proving this one why it is in phase of these two quantities. And let's prove and derive for the formula of the power. So, as you can see, as the voltage, which is in color blue, rises, the current also rises. So, much more than the power, which rises the highest or the maximum point. So, as it goes down, the voltage and the current only decreases, but the power only goes to the x-axis. The power is only at the x-axis or above the x-axis, because when you will see later why it will happen that it will not go down the power. So, let's tackle more about the purely resistive circuit. So, purely resistive circuits, its power is dissipated by the resistors. And the phase of the voltage and currents remains the same. And the current is in phase with the voltage. So, in the DC source, the formula for finding the voltage is V is equal to IR. So, instead of using V, let's start using E, or that is what we call as the electromotive force. So, let's derive the formula of how to find, or what are the formulas of finding the current, the voltage, and power when applied in AC source. Our formula of voltage in a sinusoidal form is V is equal to the maximum voltage multiplied by the sine omega t. As we know, in the DC source, we have a formula of voltage is equal to IR. So if we try to find the current, it will be equal to voltage over R. Now, if we change this formula from here, then it will go to current is equal to V of M all over R sine omega t. Now, I have written here the I, which is wrong. Well, when we only use this I if it is in a DC source. So let's change this one, since it is now in a sinusoidal form, that it will become 2 small I. So, take a look of the difference between a big I and a small I. Now, let's proceed to the derivation of power in a purely resistive circuits applied in a AC source. So, recall, we have a sinusoidal voltage which is equal to the maximum voltage sine omega t. And also, we have the current which is equal to Vm over R sine omega t. But it is also equal to the maximum current multiplied by the sine omega t. Now, let's proceed to the derivation of power. Since power is equal to IV or IE, then we substitute the two values. So we have quantity Vm sine omega t multiplied by the maximum current sine omega t. Vm sine omega t, which is equal to the sinusoidal voltage, and I, which is equal to the maximum current multiplied by sine omega t. So, it will be equal to Vm Im sine squared omega t. But it is just equal to, if I just put here 2 and also here. So, it will be just cancelled, so it's just the same. Now, we take the substitution of this one. Since sine square omega t, 2 sine square omega t is just equal to 1 minus cosine 2 omega t. Take a closer look. So, we'll substitute the value 1 minus cosine 2 omega t from the general equation. So, we have V of m, Im, all over 2 times 1 minus cosine 2 omega t. Now, it can also be equal to Vm all over square root of 2 times the Im all over square root of 2, which will just equal to the value of here, which is 2 times 1 minus cosine 2 omega t. Now, by distributive property, so it will now be equal to V of m all over square root of 2 times I of m all over square root of 2 minus V of m all over square root of 2 times I of m all over square root of 2 cosine 2 omega t. So that's it. So we'll just simplify to cancel out the parentheses. So it is now equal to V of m over square root of 2 times I of m over square root of 2 minus V of m square root of 2 I of m square root of 2 cosine 2 omega t. So this is the formula of finding the power in a purely resistive circuit. So let's continue for the average power in a sinusoidal wave of a purely resistive circuit. So we'll just copy the sinusoidal formula of power in a purely resistive circuit. So which is P, which is equal to V of m over square root of 2 times I of m all over square root of 2 minus V of m all over square root of 2 I of m all over square root of 2 cosine 2 omega t. Now, if it reaches the maximum, then we will get the average value of power. So when cosine 2 omega t reaches the maximum, which is 90 degrees, which would be equal to 0, then the average power will be equal to V of M all over square root of 2 times I of M all over square root of 2 minus 0. But this one is also equal to the VRMS. And also this one. This would be equal to IRMS. So that would be the power, average power of a purely resistive circuit. RMS, which is also a root mean square of the voltage supply and root mean square of current supply. Now let's proceed to the derivation of P maximum. We have already solved the P average. We have also solved the instantaneous power. So let's proceed to the P max. So P max is unknown. But we have also the initial conditions of VRMS is equal to V max all over square root of 2. And IRMS is equal to I max all over square root of 2. To get the P maximum, we need to get the maximum voltage multiplied by the maximum current. So, we first derive the formula for V max. So, V max would be equal to square root of 2 multiplied by VRMS. And for I max, it would be equal to square root of 2 times IRMS. So, we'll plug in the following formulas. So, P max will then be equal to I max times V max, wherein I max is equal to square root of 2 IRMS times square root of 2 VRMS. But the square root of 2 multiplied by the square root of 2 would be equal to 2 and multiplied by the IRMS times VRMS. So that would be it. That would be the maximum power formula of a purely resistive circuit. So the solution for letter A is P Ave is equal to IRMS times the VRMS with a initial condition of P average power, which is equal to 4.8 kilowatts, the voltage of 100 volts, and a frequency of 25 hertz. We can consider that the voltage in here is the VRMS. So in finding the current, we will have the average power divided by the VRMS. So substituting the values, we have a 4.8 kilowatt divided by the 120 volt, it will result to 40 ampere. Now next, we have the instantaneous maximum value of power. Since maximum power is equal to 2IE. So, 2 times 40 ampere times 120 volts, which would result to 9,600 watts. For letter C, which is asking for the resistance of the load, we can get the answer by R is equal to E over I. So, the E in here is also equal to the VRMS, which is equal to 120 volts, divided by 40, which would result to 3 ohms. In my second discussion, I will discuss all about the purely inductive circuits. So in a purely inductive circuits, the current lags behind by the voltage by pi over 2 or 90 electrical degrees. So if we go to the diagram here, we can say that when the voltage is rising, the current still in the decreasing mode. So in the positive, while the current is in the negative. But the power has a negative and also a positive value. So we will discover why it happens to be like this. And let's try to discover the derivation of power and current, and the same as the voltage and the inductive reactance in this kind of circuit. In the inductance circuit, when a sinusoidal voltage is impressed across a pure inductance, the resistance of the coil is considered to be negligibly small. So in an RL circuit, in the DC circuit, we have an E, which is equal to I times R plus L, which is in Henry, derivative of current over time. Now, consider that the R is equal to 0 and E in here is in a sinusoidal wave. So we have, or the impressed EMF, so we have here E is equal to L di over dt, or which is also equal to maximum voltage sine, since the impressed voltage would be equal to L di over dt, or just equal to the maximum voltage sine omega t. Now, in finding the current, we will use the integration in here. So, di would be equal to E of M, which is also the impressed voltage, or here, we can also say it in here. So, E of M sine omega t all over L. Now, integrating. So, we have here the impressed current, which would be equal to negative E of M all over the omega L cosine omega t. Since E of M all over omega L is equal to sine over times quantity minus pi over 2, since cosine omega t is equal to sine omega t minus pi over 2. So this would be the formula of finding the impressed current in an inductive circuit. Now, as discussed earlier in the last chapter, inductive reactance is equal to omega L, which is also equal to the voltage all over current. So therefore, its unit will be in ohms. Now, inductive reactance is equal to omega L, which is also equal to 2 pi times the frequency times the inductance. The L in here is in Henry, the F in here is in Hertz, and this is the full cycle, which is equal to 180 degrees. Boss. So let's proceed to the derivation of instantaneous power in an inductive circuit. So as we all know, P is equal to IV. Now, refer to the diagram. As you can see that the voltage is increasing, so therefore it takes a value of positive value. So, let's put it in here. So, since V is equal to E of M sine omega t. And since the current is lagging by 90 degrees, so therefore, it is in the negative sign. So take a look of the pink line. So it started with the negative sign. So therefore, our current in here, it would be equal to the negative I of M cosine omega t. Now, let's plug in the values of V and I. So we have in here negative I of M cosine omega t multiplied by E of M sine omega t. Or it will also be equal to the negative E of M I of M sine omega t cosine omega t. Now, it can also be rewritten in this way. E of M I of M over 2 times 2 sine omega t cosine omega t. Since the negative E of M, I of M, sine omega t, cosine omega t can also be rewritten into a negative E of M, I of M over 2 times 2 sine omega t, cosine omega t. In here, there is also another substitution that we can do. This is equal to sine 2 omega t. So, bring back the equation. We will have the negative E of M, I of M over 2 sine 2 omega t. Now, this one can also be written into negative E of M, I of M, all over square root of 2, times 2 sine 2 omega t. It can also be written into negative E of M over square root of 2 multiplied by I of M all over square root of 2 times the sine 2 omega t, which will be equal to the E RMS, which is the value in here, and IRMS, which is the value of also of here, this one. So, this will be our instantaneous power in an inductive circuit. Now, in finding the average power, as you can see that the power comes from the negative sign. So negative, so we'll have average is equal to negative power plus the positive power minus the negative power again, and the positive power, and so on and so forth. Then the average power would be equal to 0. period. So, example number 2, we have an inductance of 0.106 Henry is connected to a 120 volt 60 cycle source. Calculate the inductive reactance, the current in the circuit, the average power taken, the maximum power delivered to the inductor or returned to the source, the current, and the power. So, solution for letter A. Since XL is equal to 2 pi FL. Now, we have here the given of L, which is equal to 0.106 Henry, the F, which is 60 cycle, and the voltage of 120 volts. So we can solve now for XL. XL will be equal to 2 pi times 60 times the 0.106. So it will be equal to 40 ohms. Solving for letter B. How do I get this I, which is equal to E over XL? So let's derive it. So from the derivation before, we get that the omega L is equal to E over I. So therefore, I is equal to E all over omega L. But this omega L is the inductive reactance. So therefore, I is equal to E all over XL. Now, go back to the question, which is the current in the circuit. So, we have already a value of the voltage, which is equal to 120 volts, divided by the inductive reactance, which is equal to 40 ohms. It will give a result of 3 ampere. Next, solving for the average power taken. As what I have mentioned before, that the average power of an inductive circuit is just equal to 0. So that's it. That's the answer for letter C. Now, let's go to letter D. For letter D, we want to get the maximum power delivered to the inductor returned to the source. So, we have maximum power is equal to EI. Now, so substituting the values, we have 120 volts multiplied by 3 ampere. So the maximum power is equal to 360 watts. For letter E, we want to solve the current. Since the sinusoidal current is equal to I is equal to E of M all over omega L sine omega T minus pi over 2. Now, we need to solve the value of omega. Since omega is equal to 2 pi f, then 2 pi times 60 is equal to 377. That's the value of omega. So substituting the value, we have I is equal to 120 volts all over, we have 377 times 0.106 sine 377t minus pi over 2, which is equal to the 3 square root of 2 sine of 377t minus pi over 2. So, let's solve the power. Since the sinusoidal power is equal to negative of E of I sine 2 omega t. We have already find the value of omega, which is equal to 377. So, P is equal to the negative 120 times 3 sine 2 times 377 times t. So therefore, power is equal to 360 sine 754 t. So that would be the discussion of the purely inductive circuit. Purely capacitive circuit. So, try to look at the diagram in here. As the voltage or the AC source flows, the capacitor is connected to a sinusoidal source EMF, and it will continually go through periods of charge and discharge, and will moreover under periodic polarity changes. Also, the current variations will be sinusoidal, but unlike the resistive circuit, the capacitive circuit, in here, the current will lead the voltage by pi over 2 or 90 electrical degrees. Also, the voltage peaks 90 degrees after the current peaks. One builds as the other falls and vice versa. Another is that the diminishing current I builds charge on the C, which is the capacitor, which increases the back EMF of VC. When we say back EMF, when the capacitor is fully charged, it will again distribute the charge from the capacitor to go back to the source. Previously, it was discussed in the RC circuit that the voltage is equal to the current times the R plus the integral of the integral of I dt over C from limits 0 to t. Now, if we apply the AC source in here, the E would be equal to the maximum value of voltage times the sine omega t, which is equal to integral of I dt over C from limit 0 to t. Consider in here that the value of resistance is 0. So, I times 0 is equal to 0. So, it was cancelled out already. So, or it can also be written as maximum value of M times sine omega t is equal to 1 over C integral of I dt from limit 0 to t. Now, if you could just recall that in this part, this is equal to charge. So therefore, charge is equal to C times maximum value of voltage times the sine omega t. Now, since the charge is In a sinusoidal, it goes through time. So therefore, dq over dt is equal to omega sine E of m cosine omega t. It was already derived. So we have in here, since sine omega t, which is equal to sine derivative of sine omega t is equal to omega cosine omega t. So let's continue. Now, in here, in this part, this is already the sinusoidal current, which is dq over dt. So therefore, I is equal to omega times the capacitance times the maximum value, and since cosine omega t is also equal to the sine or quantity omega t plus pi over 2. Now, in getting the maximum current, proceeding that the sine of omega t plus pi over 2 is in maximum, then the maximum current will be equal to omega times the capacitance times the maximum voltage. Previously, it was discussed all about the inductive reactance. Now, let's also proceed to the capacitive reactance. In here, we will use the XC prime, which means that the C prime in here is in the unit of farad. So therefore, since XC prime is equal to 1 over the omega C prime, which is also equal, since this is also equal to 2 pi f C prime ohms. Moreover, most of the books are using the microfarad. So therefore, it's also equal to 10 to the 6th all over 2 pi f C. Since in here, the C is already microfarad. So the unit is still in ohms. The waveform of a capacitor circuit. So, take a look. The current starts in the negative side. So therefore, it will take the value of cosine omega t. And the value of voltage is in the upper hand, which it is in a rising mode. So therefore, it will take a value of the sine omega t. So, let's derive the formula of an instantaneous power in a capacitive circuit. So, we all know that power is equal to IV. Now, since the current is in a negative side, that it starts in a negative side, so therefore, I of m cosine omega t multiplied by the voltage, which is E of m sine omega t. Now, it will also become 2 E of m, I of m, cosine omega t, sine omega t. It can also be rewrite into E of m over 2 times I of m over 2 times 2 cosine omega t sine omega t. Since this one is equal to sine 2 omega t, and we can also rewrite these two into E of m over square root of 2 times I of m all over square root of 2 multiplied by sine 2 omega t. So this will be the formula of finding the instantaneous power of incapacitive circuit. Now, if we try to find the maximum, the average power in a capacitive circuit, then P average is equal to, looking back to the diagram, notice here of the power which is in the pink color. So it started in the upper hand. So it will give a value or yield a value of positive P. Then it goes down. So therefore, the value of power will also be a negative P. And then it rises again and go down. So therefore, average power will have a positive P minus P plus P minus P and so on. So therefore, the average power of a capacitive circuit is also equal to 0. The same as for the inductive circuit. So, example number 3. In a capacitive circuit, so we have a 127 microfarad capacitor is connected to a 125 volt, 50 cycle source. Calculate, letter A, the capacitive reactance. Letter B, the current in the circuit. Letter C, the average power taken by the capacitor. Letter D, the maximum power delivered to the capacitor or returned to the source. Letter E, which is the current. And letter F, the power. So let's start with letter A. Since the capacitive reactance is equal to 10 to the 6 all over 2 pi f c, which has the given values of C, which is equal to 127 microfarad. We have an E, which is equal to 125 volts, and a frequency of 50 cycle. So, plug in the given data. So we have 10 to the 6th all over 2 pi times 50 times 127, which is equal to 25 ohm. Solving for letter B, the current in the circuit. So, I is equal to E over XC. So, plug in the given datas. We have 125 volts divided by the capacitive reactance, which is 25 ohms. It will give a result of 5 ampere. Next, the average power taken by the capacitor. Since the average power as of before will just give us a result of 0. So therefore, average power is equal to 0. And then we have to find the maximum power delivered to the capacitor or returned to the source. Since maximum power is equal to E max times I max. And we have here E max of 125 volts multiplied by 5 ampere, which is equal to 625 watts. Solving for letter E, the current. Since the sinusoidal current is equal to omega C of C times E sine of omega t plus pi over 2. Now, solving for the omega, which is equal to 2 pi f, so 2 pi times the frequency, which is 50 cycle, it will give us a 314 value. So, 314 times the capacitance, which is 127 times 125 sine 314t plus pi over 2, which is equal to 5 square root of 2 sine 314t plus pi all over 2. Now, solving for f. The power. Since power is equal to E of I sine 2 omega t, so we plug in the values. We have E of 125 volts times 3 ampere times the sine of 314 times 2 t. So, the answer would be 625 sine 628 t.
Sakit niya. Pepe.
Oh, tapi dua.
Don't stress your mind.